In this video, we're going to cover two of the sections out of chapter 7. So we're going to be looking at the Laplace transforms, and we're going to look at that through sections 1 and 2 out of chapter 7. There are 10 problems that I'm going to work through here with you. And so hopefully you'll find this video helpful as you study for the quiz and our third exam. Okay. So the first problem that we're going to look at comes from section 7.1. And really, we're just trying to find that Laplace transform, okay? And just as if you haven't looked at the text yet or anything like that, that is, we can say that our Laplace transform is equal to the integral from 0 to infinity of e raised to the negative st times our function f of t. And so again, that is the Laplace transform. Now you'll see this particular set of problems says that you need to use definition 7.1.1. Right? You can find this on page 279 of your textbook. Okay, so for this first problem here, we are given a function. So this is problem number 12. So we would say that our Laplace transform is equal to the integral from 0 to infinity of e to the negative 2t minus 5 times this e to the negative st. You could have done it either way. You could have put the e to the negative st first and then the function that we were given. It's multiplication, so it doesn't really matter. Okay. We're going to rewrite this a little differently. We're going to break this piece right here up. So we can write that still as e to the negative 2t and then e to the negative 5, e to the negative st. So it's all still the same. We're just breaking it out. The reason we're doing this is because you'll notice this piece right here does not have the t with it. So we could actually pull that out to the front here. So that's going to give us e to the negative 5, then the integral of from 0 to infinity of e to the negative 2t e to the negative st dt. Okay, we could then bring those two pieces together as well, right? Just by using rules of exponents. So that's going to be e to the negative 5 integral from 0 to infinity of e. I'm going to factor out a negative from that. So if I take a negative from this first term, and we'll do like a negative t actually. Let's make that a little cleaner. If we factor a negative t out of that, that leaves me with the positive 2 here. In the second term, it'll leave me with an s. Okay. And then finally, we take that integral. That's going to give me e to the negative 5 over 2 plus s times e to the negative 2 plus st. And we want to evaluate this from 0 to infinity. And when we do that, we end up with e to the negative 5 over 2 plus s. And we need to just ensure that s is greater than negative 2. Okay. Here is another example of the same kind. So we'll look at that using that same definition 7.1.1. So we have our Laplace transformation is equal to the integral from 0 to infinity of t times sine of t. times e to the negative st dt. Okay. So when we take that integral, this is going to be a little bit longer, but when we take that integral, we end up with our negative t over s squared plus 1 minus here over s squared plus 1 squared times our cosine of t times e to the negative st. We also, that's when we plug in, when we take the first half, but we also have to keep going, and we end up with minusing off the st over s squared plus 1 plus s squared minus 1 over s squared plus 1 squared times our sine of t e to the negative st. We're going to evaluate that from 0 to infinity, and that simplifies then to 2s over s squared plus 1 squared, and so our s has to be greater than 0. Okay, so still in chapter 7.1, but we're moving to a new section type of problems. This time, instead of definition 7.11, we're going to use theorem 7.1.1, and you can find that in your textbook on page 282. Okay, for this particular problem, we're actually going to use rule B, as in boy, right? So we're going to use the second rule there. And so we have that our Laplace transform negative 4t squared plus 16t plus 9, right? That's our function. And so using definition B off of this theorem, we would get 8 over s cubed plus 16 over s squared plus 9 over s. Okay. Another example from this time we're going to use E and D. And so for this one, we have our Laplace transform at cosine 5t plus sine 2t. Okay. Using E and D for this, we're going to get s over s squared plus 25 plus 2 over s squared plus 4. Okay. Now we're moving into chapter 7, section 2. So this is where we're going to start looking at the inverse Laplace transforms. And so for this one, inverse, this is going to be 4 times 1 over s plus 1/4 times 4 factorial over s to the 5 minus 1 over s plus 8. And I'll point out here that this is saying that a is equal to 1, okay? Or we're using that definition there in the theorem. And so that tells us that it's equal to 1. This second term, we're actually using the b, and that tells us that we're using t raised to the n. And in this case, our n has to be, our n is 4, okay? Because if you look at the transform, this right here is f plus the s raised to the n plus 1. And so if it's s raised to the 5, that means n has to be 4. And then for this term, we are using the C1, and that is giving us the e raised to the at. And in this case, a then is going to have to equal 8 because that would be s minus a is what it is. So s minus a negative 8 to keep it in that same true format. Okay. So now that we have all of that, we can simplify and say that this is 4 plus 1/4 t to the 4 minus e to the negative 8t. Okay. For this next portion, we're going to use, so this tells me we're looking at that formula E, which tells us that we're going to use cosine of kt. So this is where, in this case, right, our k squared is equal to 16. So our k has to equal 4. So this then would give us 10 cosine of 4t as a solution. Okay. Still working with inverses. So this we can actually factor this denominator. That gives me s minus 4, s plus 5. Okay. So when we're looking at our inverse Laplace transform, that is going to be 1 over s minus 4, s plus 5. Okay. And so that gives us 1 over 4 minus 5 times e to the 4t minus e to the negative 5t. And we can simplify that to 1 over 9 times e to the 4t minus 5. E to the negative 5t. Okay. For this one, we're going to use our Laplace transform to solve the given initial value problem. Okay. So this is, we have 2 times our Laplace formula with y prime plus Laplace of y equal to 0. Okay. So we could factor that 2 out, right? So that's going to give me 2 times s, my Laplace of y, minus y naught, plus our Laplace of y equal to 0. Okay, we were given that y of 0 is equal to negative 3. So 2 times s y minus this negative 3, that's our y naught, plus equals 0. So let's simplify this down a little bit. This gives me 2s Laplace of y plus 3. Actually, we have to, let's distribute that. So it's going to be plus 6 plus Laplace of y equals 0. What we'll do here is let's get that 6 on the other side. Let's get that on the other side, and that will leave us with 2s of y plus the Laplace y equals negative 6. Okay, we can factor out the Laplace transform here times 2s plus 1 is equal to negative 6. So let's get the Laplace of y by itself, and that's negative 6 divided by 2s plus 1. Okay. And that is the same as if we pulled that -3 out again, and we have 2 over 2s plus 1, right? We can simplify that, the stuff inside the parentheses a little more, and say -3, so our y equals -3 times 1 over s. We're really just, that gives me s, and then that would give me plus 1/2 over here if we did that, if we're just breaking out the two. And that the reason we do that is because this then gives us a format of function e, or rule e, where we have e to the at, where our a equals -1/2. So then our equation here would be y equals -3e to the -t over 2, because our a is -1/2. Okay, another one of those type of problems. So we have y prime minus y is equal to 2 cosine of 5t. We can break this out. So we have y prime minus the y. And we can bring the 2 on the outside because it's a constant, right? So we can bring that out. So we have 2 cosine of 5t. Okay. Now we can simplify this a little bit more. In doing so, when we have the Laplace of a y prime, that's the same as saying s of just our y minus L of y equals, and then we can make this transform. It would be 2s over s squared plus 25. So we're really just moving that into the transform already. So this one we can factor the Laplace transform of y, and that leaves us with s minus 1. Okay, now we can divide both sides by the s minus 1. Clean that up a little. S squared plus 25. Okay, so we can set that in a similar form where we would have a, when we're looking at the partials, over s minus 1 plus bs plus c over s squared plus 25. So we have 2s is equal to a times s squared plus 25 plus bs plus c times s minus 1. So when we're looking at that first one here, right, or this one, when we say s is equal to 1, then when we solve that out, then a is equal to 1 over 13. And when s is equal to 0, right? So if s is equal to 0, then we're going to end up with our c value is equal to 25 over 13. And if we let s equal to -1, then we will get that our b value is equal to -1 over 13. Okay. So that gives us, let me go to the next page. That gives us our y of s formula equal 1 over 13 times 1 over s minus 1 minus 1 over 13 times s over s squared plus 25 plus 25 over 13 times 1 over s squared plus 25. Okay, so we have that. And now let's take our inverse Laplace transform, okay, of this function y of s. Okay, so that is going to be 1 over 13, our Laplace inverse of 1 over s minus 1 minus 1 over 13 Laplace inverse of s over s squared plus 25 plus 25 over 13 Laplace inverse of 1 over s squared plus 25. Okay, so let's decompose a little bit of the things that we need. We know for this first one here, right, that's like the format of C. So that means we need e raised to the AT, with a being equal to 1. Okay. For this one, that looks like the form of part E. So that's giving me, that's the cosine of KT, where our K in this case is going to equal 5. Now this piece here, because we don't have a 5 up here, it doesn't quite match our things. So what we can actually do is take a 5 from here. We can leave 5 out here and put 5 in here, because when you multiply them, you still have that 25. This is like form D, where we have our sine of KT and our K is equal to 5. Okay, so when we do that, we're left with 1 over 13 e to the t minus 1 over 13 cosine 5t plus 5 over 13. Remember, we had to borrow a factor of 5 for inside the function, and then sine of 5t. Okay. All right, the last problem I have to work as an example for this evening is number 39. So we have our y double prime plus 5 times Laplace of the y prime plus 4y equals just Laplace of 0. Okay. So for this one, that's our s squared Laplace, because it's 2 times removed, right? So it's a double prime plus 5s Laplace y plus 4 equal to 0. Okay. All right. So one of the things that we can do here is we can actually let's go back to the blue. Scoot that over just a little bit. Because of the second derivative, we're minusing off s here and minusing off that 5. Okay. And we want to actually move those to the other side. So we're going to add the s and we're going to add the 5 to the other side. to get us, and then we'll factor also in the same time. Let's factor out the Laplace y. So that leaves us with the s squared plus 5s plus 4 equals this s plus 5. Okay, so our y is equal to the inverse of that. And so this is s plus 5 over s squared plus 5s plus 4. Okay, that denominator will factor. This factors to s plus 4, s plus 1. So we could set that up in the form of a over s plus 4 plus b over s plus 1 equals s plus 5 over s plus 4, s plus 1. Okay? So a times s plus 1 plus b times s plus 4 is equal to s plus 5. So when our s is equal to -1, then we have 3b equals 4. Therefore, b is equal to 4/3. And when we have s is equal to -4, we have -3b is equal to 1. I mean, not b, a. And therefore, this one is, yeah. And then we end up with a equals -1/3. Okay. And then finally, when we put that all together, we have y is equal to our Laplace inverse, -1/3 over s plus 4 plus Laplace inverse of 4/3 over s plus 1. So y is equal to -1/3 e to the -4t plus 4/3 e to the -t.